morning, everyone. Today, we will explore entropy, a fundamental concept in thermodynamics that explains why certain process occurs naturally and others do not. Let's break down its definition, its significance, examples, and historical roots. So, first of all, what is meant by entropy? Entropy is a measure of disorder or randomness in a system. It was first introduced by Rudolf Clausius in the 1850s. It quantifies how energy disperses during a process. In thermodynamic terms, entropy helps to predict the direction of spontaneous changes, such as heat flowing from hot to cold or gases mixing irreversibly. Mathematically, entropy change for a reversible process is given by delta S is equal to the amount of heat transfer divided by temperature. And here the heat transfer is a reversible process and the temperature we have to take it in Kelvin. Now here why entropy is an important term. The second law of thermodynamics states that the total entropy of an isolated system always increases over the time. This principle explains why natural process becomes irreversible. We can take an example. If a glass is shattered, it doesn't resemble itself again. And the systems evolve towards the equilibrium. Example, ice melts in a warm room until the temperature equalizes. That is the temperature of water and the room temperature. Entropy also governs the feasibility of energy conversion. For instance, heat engines can't achieve 100% efficiency because some energy disperses as waste heat, increasing its entropy. Now take certain examples where there is we can say change in the entropy. The first common example is melting of ice. When ice melts into water, entropy increases as rigid molecule structures break into disordered liquids. The second example is mixing of gases. If helium and argon are released into a container, they mix spontaneously. Once mixed, they cannot be separated. Hence, there is an increase in the entropy in this system. Third example is heat transfer. If a hot coffee cup cools as the heat flows to the cooler room, this causes or this is the natural direction of energy dispersal, which align with the increase in the entropy of the systems. Now, the historical context of this entropy goes very back when the scientist Rudolf Clausius coined the term entropy while studying the heat engines and the Carnot cycle. His work revealed that while the energy is conserved as per the first law, its usefulness diminishes due to entropy-driven irreversibility. Later, Postman linked entropy to molecular disorder, defining it statistically as S is equal to K ln of omega, where the omega represents the number of microstates. Now, why it matters the most? Now, the understanding of the entropy allows the engineers to design efficient systems such as power plants, refrigeration cycles, predict environmental impacts of the energy use, innovate sustainable technologies by minimizing the entropy productions. In essence, entropy isn't a measure of chaos. It's universal driver of natural process shaping everything from ice melting to the universe's eventual heat rate that we will discuss in the coming slides. Now we are going to explore what is entropy and its role in thermodynamic systems, and then how entropy is going to affect or govern equilibrium, irreversibility, and the evolution of natural process. Now, considering entropy as a state function. As we all know, entropy is a state function, which means it depends only on the current state of a system, not on how it got there. Think of it like your bank balance. It reflects your current funds, not whether you earn them through a paycheck, a gift, or a lottery win. So here, simple terms, the change in entropy is given by what is the final value of entropy minus the initial value of entropy. The change in entropy depends solely on the system initial and final states and not the path which is taken by the systems. Now here, if we consider the equilibrium and the maximum entropy, the second law tells us that isolated systems evolve towards equilibrium, which means entropy becomes maximum. At equilibrium, temperature, pressure, and density gradients vanishes, and there is no further spontaneous change which is going to occur. For example, if you open a pressurized gas tank in a vacuum, the gas molecules rush out until pressure becomes equal. Once the equilibrium is reached, that is, the pressures are equal, entropy cannot increase further. Now take a real world example of ice in a warm room. And if you imagine a glass of ice water left in a warm room, then we will see what is going to happen to the entropy. So let's start one by one. So the first process is the ice melting. As the ice melts, the entropy increases as rigid ice becomes disordered liquid water. Next is the heat flow. Now here, the heat transfer occurs from the room, which is at a high temperature, to the glass, which is at a low temperatures. Therefore, the change in the entropy, or there is a decrease in the entropy of the room, which can be given by delta Q divided by T. Delta Q is the, we can say, heat transfer, okay, and T is represents the temperature. Now here there is a decrease in the entropy because we are considering here the Q as minus. And on the other hand, the entropy of the glass, okay, which is going to increase. Why? Because there could be a heat rejection, and here this heat rejection we take as a positive value divided by the temperatures, okay. So here if we take the total entropy of the system, that is entropy of the glass plus the entropy of the room, okay, so it is equal to 0, okay. Therefore, if we see, even though the room loses or there is a decrease in the entropy of the room, the overall entropy of the isolated system, that is the system and surrounding, always increases. And why this matters? That is a most important question, because their answer lies in the term which is known as irreversibility. Now in this case, if you see, the ice water system won't spontaneously refreeze unless external work like a refrigerator reverses this process. The refrigerator will be used to convert water into ice. And the engineering insight in this, now take an example of power plants and engines. They must account for the entropy production to minimize waste and maximize efficiency. Now here, think of entropy as nature's mass meter. If a system left alone will always tend to chaos, means it will become a untidy. Like a tidy decks, inevitably there is a clutter over the time, and you need to clean these decks. That means you need to reduce the entropy, and for that you need energy, that is work. Therefore, entropy isn't an abstract concept. It is a measurable property that dictates how energy disperses and systems evolve. By understanding entropy role in equilibrium and irreversibility, engineers can design smarter systems that aligns with nature rules. Now we will explore Clausius' groundbreaking definition of entropy and how it quantifies the second law of thermodynamics. So the Clausius definition of thermodynamics is given by delta S is equal to Q reversible, that is the heat transfer in a reversible process, divided by T, which is absolute temperature in kelvins at which this heat transfer occurs. Now, this equation links entropy to heat flow and temperature, formalizing why natural processes have a directional arrow time. Here, why heat flows from hot to cold? That becomes an important question. When the heat flows from hot objects, which is at a high temperature, to the cold object, which is at the low temperature, in this case, the entropy is gained by the cold object. Okay, why? Because delta S is equal to dq by T. Here, since the cold object gains the heat, this heat is a positive. Okay, and the entropy which is lost by the hot object, delta S hot, is given by minus dq by T. Now here, what is going to happen? Here, this entropy is going to increase. Okay, and here the total entropy is how much? The entropy of system plus entropy of surrounding, and that is greater than 0. Now here comes the important concept of reversible and irreversible process. Now in case of a reversible process, which is identified as an infinitely slow process, the total entropy change is 0. That means system plus surrounding total entropy is equal to 0 for the reversible process. Now in case of an irreversible process, these processes are the real world process which requires a finite amount of time, and for this process the entropy always increases. Okay, so in case of a melting of ice, if you consider this is an reversible process. Why reversible process? Because if you take an example where ice melts, what is going to happen? If ice is going to melt, so there is certain heat of the ice. We call it as a latent heat of fusion. Okay, when this ice melts, it takes the latent heat from the surrounding, and this latent heat is responsible for conversion of ice into water. And this amount of heat is having certain standard value, that is around 334 kilojoules, and this process occurs at 0 degrees centigrade, and during this process the temperature remains constant. Now what is going to happen for this process? Now the entropy change of the ice is given by dq by t, that is 334 kilojoules divided by 273, that comes around, it is around 1.22 kilojoules per Kelvin. Now on the same way, the atmosphere or the surrounding is giving heat to the ice. Therefore, this heat which is going from the surrounding, we take as a negative value of minus 334 kilojoules divided by 273, that comes around minus 1.22. So what is going to happen? Now here in this case, the total entropy change is nothing but summation of entropy change of ice plus entropy change of surrounding. So it becomes positive 1.22 minus 1.22, that gives us 0. Therefore, since the entropy change becomes 0, we say this process is a reversible process. Okay. Now, why this matters the most? Because we have to predict the process feasibility. If a process reduces the total entropy, that is heat flowing from the cold body to hot body, which is impossible without the external work, for example, a refrigerator. And efficiency, or in case of a reversible process which represents a Carnot cycle, the efficiency is maximum, and the real systems aims to have the efficiency which is less as compared to this Carnot cycle efficiency. Now we take an example, or we take a simple correlation of an entropy as a tax collector. Means in our India, the government or central government is collecting the tax. Now think this entropy who is a tax collector. Now in this case, if you see, every energy transfers pays an entropy tax to the nature. So whatever you go in the market, you buy something, there is a tax associated with it. Okay, and this goes to government. Therefore, whenever there is an energy transfer and there is a, we can say, the entropy tax to the nature. Now for the reversible process, pays 0 tax. So that we can say it is an ideal case. And irreversible process pays extra tax. That is, large amount of energy is wasted. Okay. Therefore, the closest definition of entropy, this is nothing a simple maths. It is a tool to decode why engines have efficiency limits, why perpetual motion machines cannot exist in nature, and why the universal tends to have more disorder day by day. Okay, by mastering these concepts, we can design systems that work with nature rules and not against them. Okay. Now we will see Boltzmann statistical definition of entropy. Boltzmann statistical definition of entropy is a revolutionary concept that links thermodynamics with statistical mechanics. This perspective not only enhances our understanding of entropy, but also explains why systems naturally evolve towards higher entropy states. Now, Boltzmann defined entropy in terms of number of possible microstates of a system using the equation S is equal to K natural logarithmic of omega. S is the entropy, K is the Boltzmann constants, its value is approximately 1.38 into 10 raised to minus 23 joules per Kelvin, and omega represents the number of microstates corresponding to a given microstate. This formula reveals that entropy is fundamentally a measure of disorder at the microscope level, relating macroscopic thermodynamic properties to the underlying statistical behavior of particles. Now, what are the implications of the Boltzmann definitions? The first one is regarding the statistical basis for entropy. Higher entropy corresponds to a greater number of microstates. For example, a gas in a container has higher entropy when its molecules are distributed throughout the volume rather than clustered in one form. The systems naturally evolve towards configuration with more microstates, leading to increased disorder and higher entropy. Second is understanding the spontaneous process. Now, the Boltzmann definition provides insights into why certain processes occur spontaneously. For instance, mixing two gases increases the number of possible arrangements or the microstates, thus increasing the system's overall entropy. Now, taking an example of mixing two gases, now consider if two different gases, say helium and nitrogens, which are initially separated in a container, are mixed. When mixed, each gas occupies any position within the container, vastly increasing the number of possible microstates. Before mixing, each gas has limited arrangement based on its confined space. After mixing, the total number of arrangements increases significantly because each molecule can now occupy any position in the entire volume. As a result of this, the entropy of the mixed system is greater than that of a separated system. This increase in entropy aligns with the second law of thermodynamics, which states that the total entropy in an isolated system tends to increase over time. Now, why it matters the most? Now, if we are going to connect the micro and the macro properties, the Boltzmann approach bridges microscopic particles' behavior with the macroscopic thermodynamic properties, providing a deeper understanding of the physical phenomena. Now, this application of this statistical mechanics includes, which is a foundational in statistical mechanics, that this definition of this Boltzmann is foundational in statistical mechanics, which allows us to derive thermodynamic properties from microscopic principles. And consider this entropy with another term, which is called as, we can say, the information theory. Now, the Boltzmann idea have implication beyond physics, and that can be extended to the information theory, where entropy quantifies uncertainty or information contents. Now, imagine a library where books are organized by their genre, and this state we call as a low entropy state, versus the other state where books are scattered. Okay, no, we can say when these books are scattered, we are not considering their genre, means they are not organized by their genre, by their classification, etc. Now, this state we call as a scatter state, as a high entropy state. Okay, now the more ways you can arrange the books, okay, means the more microstates, the higher the entropy. Just like how system naturally tends toward the disorder, librarians often end up with messy without effort. Means these scattered books when they have to get them organized, they have to put certain efforts for the librarians. Okay, so this is the, we can say, a classical example of the entropy or the state of disorder. Now here, the Boltzmann statistical definition of entropy provides profound insight into why systems evolve towards the higher entropy states and how microscopic behavior influence macroscopic phenomena. By understanding this relationship, we can better comprehend not only thermodynamics but also various fields where and disorder, where order and disorder plays a crucial role. Now, let's look on another important topic, which is known as second law of thermodynamics and entropy. Now here, the second law of thermodynamics has profound connections with entropy. This law is fundamental in understanding the behavior of energy in natural process and its significant implications for engineering and technology. Now, what is the statement of second law? The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This principle highlights that natural processes tend to move towards greater disorder or entropy, making it a key concept in thermodynamics. Now, the implications of the second law. The first is irreversibility. Second law explains why certain processes are irreversible. For example, when you drop a glass and it shatters, the broken pieces will not spontaneously reassemble. This irreversibility is a direct consequence of increasing entropy. As we all know, the second law also imposes limits on the efficiency of heat engines. No engine can convert all input heat into work because some energy is always lost as waste heat, contributing to increase in entropy. Now take an example of an power plant. Let's consider a practical example of this. In a typical thermal power plant, fuel is burned to produce heat. Which is then used to generate steam that drives turbines to produce electricity. However, all the energy from the fuel can be converted into electrical energy, but some energy is lost as waste heat to surrounding. This waste heat increases the total entropy of the system, that is, the power plant and the surrounding environment, thus limiting the overall efficiency of the power generation process. For instance, if a power plant has an efficiency of 40%, it means that 60% of the energy is lost as waste heat, contributing to increase entropy in the environment. Now, understanding the second law is very much crucial for engineers while designing efficient systems. By recognizing that some energy will always be lost as a waste heat, they can develop technologies that minimize these losses and improve overall efficiency. Now, the implications of increasing entropy are essential for assessing environmental impacts. As we strive for sustainable energy solutions, acknowledging how energy transformation contribute to entropy productions help us to guide innovations in renewable energy technologies. Therefore, the second law of thermodynamics establishes that total entropy in an isolated system always increases over time, explaining why spontaneous processes lead to greater disorder and why certain processes are irreversible. Additionally, this law limits the efficiency of heat engines by highlighting the energy loss as waste heat. Now, this principle not only enhances our grasp of thermodynamic processes but also drives advancements in engineering and technology aimed at improving efficiency and sustainability. Now we will see application of entropy. Entropy plays a crucial role in various engineering and environmental applications. Here are some key areas where entropy is applied. The first is efficiency of engines. Entropy fundamentally limits the maximum efficiency of heat engines. Engineers utilize this principle to design engines that approach the Carnot efficiency limit, which is the theoretical maximum efficiency achievable between the two temperature reservoirs. By understanding how entropy increases during energy transformation, engineers can create more efficient engines that minimize waste heat and maximize work output. Now, sorry, in case of a refrigeration systems, entropy is essential in design of these systems such as refrigerations and air conditioners. These systems rely on the principle that heat naturally flows from cold to hot environments, which requires energy input to reverse this flow. By applying entropy concepts, engineers can optimize refrigeration cycles, ensuring that systems operate efficiently while transferring heat effectively from cooler interiors to warmer surroundings. Next is environmental impact. Entropy analysis helps to assess the environmental impacts of energy systems by evaluating entropy production and energy efficiency. By understanding how energy transformation contribute to entropy generation, engineers can design systems that minimize waste and reduce their ecological footprints. This approach is particularly relevant in developing sustainable technologies and assessing the long-term viability of energy solutions. Now, in case of these power plants, which utilize entropy analysis to optimize efficiency and minimize environmental impacts. By evaluating how much energy is lost as waste heat and how it contributes to increase entropy, engineers can implement strategies to enhance performance. For example, improving heat exchanger designs or implementing combined cycle systems can significantly reduce exergy loss and increase overall efficiency. Now, next is other industrial application where entropy plays a pivotal role. As we all know, entropy has application beyond traditional thermodynamics in various industrial fields. For instance, in industrial engineering, entropy-based algorithms are used for optimizing processes like dispatching of automated guided vehicles and ranking simulated systems based on performance metrics. These applications demonstrate how entropy can inform decision making in complex operational environments. Therefore, this entropy is a fundamental concept that underpins many engineering practices and environmental assessments. Its applications span from optimizing energy, or we can say engine efficiency, to designing effective refrigeration systems and evaluating environmental impacts. As we continue to innovate in technology and sustainability, understanding and applying the principles of entropy will remain essential for advancing efficient energy systems. Coming on the next important topic, that is entropy of mixing. This is a fundamental idea in thermodynamics that illustrates how mixing substances leads to an increase in entropy. The entropy of mixing refers to increase in entropy that occurs when two or more substances are mixed together. This increase in entropy is a result of the enhanced number of possible microstates available to the systems once the substances are combined. Why does this mixing increase the entropy? When two different substances are mixed, the arrangement of particles becomes more disordered. For instance, consider two gases at the same temperature and pressure. Before mixing, each gas occupies a distant or a particular volume and has a limited number of arrangement or the microstates. After mixing, the particles can occupy any position within the combined volume, greatly increasing the number of possible arrangements, that is, microstates. Now here, the increase in microstates corresponds to an increase in the entropy as described by the Boltzmann definition. S is equal to K ln of omega, where K is the Boltzmann's constant and omega is the number of microstates. Now here we can take an example as we have taken in the earlier slides, mixing of helium and argon. Okay. Now this process occurs without any net exchange of heat or work with the surrounding, and it is a spontaneous process and it is driven purely by the increase in the entropy. Now here there is a important concept which is known as the irreversibility. Once this helium and argons are mixed, this will not spontaneously separate back to their original state without any external intervention. This illustrates a key aspect of entropy, that is, its increase is generally irreversible under natural conditions. The tendency for systems to evolve towards higher entropy states reflects the second law of thermodynamics. Now, there are certain real-world applications where the entropy of mixing is having certain practical implications. In case of this chemical science or chemical engineering, designing the process that involves mixing reactants efficiently. In environmental science, predicting how pollutants disperse in air or water. In case of the food science, understands to understand how the ingredients combine and affect the flavor profiles. Now, therefore, the entropy of mixing is a critical concept that highlights how mixing substances leads to an increase in disorder and entropy due to a greater number of microstates. This principle not only illustrates the irreversible nature of spontaneous process, but also highlights applications across various scientific disciplines. Now, we will explore how entropy manifests in a real world process and why it plays a pivotal role in the spontaneity and directionality of these events. Now let's see various examples and their implications. In everyday life, many phenomena occur spontaneously due to an increase in entropy. Here are certain key examples. First one is the ice melting. When ice melts, the structure crystalline lattice of solid water breaks down into a more disordered liquid state. This increase in molecular disorder directly translates to an increase in entropy. Next is the iron rusting. Iron rusting involves the oxidation of iron atoms in the presence of oxygen and moisture. This process results in the formation of iron oxide, that is rust, which has a less ordered structure compared to the original metal ion. Consequently, the entropy of the system increases as the iron transforms into the rust. Next is the gases mixing. When two or more gases are mixed, they spontaneously distribute themselves throughout the available volume. This mixing increases the number of possible arrangements for the gas molecules, leading to a significant increase in entropy. Now, there is certain implication of spontaneity and irreversibility that we are going to see. Now here, entropy explains why this process occurs spontaneously in one direction but not in the reverse direction. Now take an example, when ice melts naturally in a warm environment due to entropy increase, but water does not spontaneously refreeze without external interventions. Iron rust over time, but rust does not spontaneously revert to iron. Gases mix, but they do not spontaneously separate back into their original volumes. These examples highlights a fundamental principle, that is, spontaneous process always proceeds in a direction that increases the total entropy of the system and its surrounding. Now here, take one example where the diamond is converting to graphite. Diamonds and graphite are both the forms of carbon, but they have different crystal structure. Diamond has a highly ordered tetrahedral structure, whereas the graphite has a layered, less ordered structure. The conversion to graphite is spontaneous because graphite has slightly higher entropy than diamond. While this transformation leads to increase in entropy, it occurs extremely slow at a room temperature due to the high activation energy barrier. This illustrates that while the process may be thermodynamically favorable, that is, it increases the entropy, its rate depends on the kinetic factors also. Now, understanding the entropy in a real world process allows us to predict the direction of spontaneous changes, design systems and processes that are more efficient and sustainable, and gain deeper insight into natural phenomena and their implications for engineering and environmental science. Therefore, the entropy is a crucial concept in understanding why certain processes occur spontaneously in nature, whether it is ice melting, iron rusting, gases mixing, or even diamond converting to graphite. The underlying principle remains the same. Entropy always tends to increase over the time, driving this transformation into a specific directions. Now, coming on to one more example where there is a connection between entropy and information technology. Now, how there is this connection between entropy and this information entropy or the thermodynamic and information entropy that we will see. As we all know, entropy in thermodynamics measures the disorder or randomness within a physical systems, while the entropy in information theory quantifies the uncertainty or randomness of information. The analogy arises from the mathematical formulations of both concepts. As we all know, the thermodynamic entropy defined by the Boltzmann equation is given by S is equal to K natural logarithmic of omega. Okay? And the information entropy is given by Shannon's equation, which is H is equal to minus summation of Pi log of Pi, where H is the information entropy, Pi is the probability, each possible outcomes, and this formula captures the average uncertainty associated with a random variable. Now here, both forms of entropy deals with the disorder, that is the thermodynamic entropy, which relates to the energy dispersion in physical systems, while the information entropy pertains to the unpredictability of data. In thermodynamic processes, tends to occur spontaneously when they lead to an increase in entropy. Similarly, in information theory, systems evolve towards configurations that maximize uncertainty or randomness. Data compression algorithms rely on reducing the information entropy to store data more efficiently. By identifying the patterns and redundancies in the data, these algorithms minimize the amount of information needed to represent data without losing essential content. Now, consider a scenario where a large data set contains repetitive information. A data compression algorithm analyzes the data set to identify the patterns. By reducing the redundancy, it effectively lowers overall information entropy. Now, for instance, instead of storing A, B, 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 C, 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 it might store as 5A, 3B, 2C, means a numerical letter with the values of same alphabet, and by using this phenomena, it can significantly reduce the space without losing the information. Now, this process illustrates how understanding and manipulating entropy can lead to more efficient data storage solutions. The analogy between thermodynamic entropy and information entropy emphasizes the universal nature of disorder and uncertainty across the different domains. Both concepts provide valuable insight into their respective fields. That is, the thermodynamics helps us to understand how energy transformations, while information theory aids in quantifying and optimizing the data representations. As we continue to explore these ideas, we can see how they interact in various applications from engineering to computer science.